Dear students, in this video we're going to talk about the Laplace transform, the frequency domain representation of a signal. Uh, in the previous lecture we have discussed about Fourier transform, which is used for your continuous signal and periodic continuous signals. Laplace transform is also used for continuous aperiodic signals, but there is a difference between these two transformations. That is, the Fourier transform is used only for the stable systems, whereas this Laplace transform can be used for both the stable and unstable systems. So it has advantage over Fourier transform, as it can be used for Fourier frequency domain representation of the unstable system too. And the equation for Laplace transform is given by using the expression as shown below. So it can be two definition, like bilateral Laplace transform and unilateral Laplace transformation, where bilateral transform is defined for two-sided signal, those signals which are defined in either range, like from greater than 0 and less than 0. Both side signals are present. For those type of signals, the equation for Laplace transform is given by equation 1. Xs is equal to minus infinity to infinity integration xt into e to the power minus st dt. So this minus s is replacing the Fourier transform's equation e to the power minus j omega t. So this s is indicator that this equation is representing a Laplace transform. So s is known as the S domain, or this is complex frequency domain. So that we will discuss in the next topic. So first we want to discuss about the equation of Laplace transform, where the second equation is given as xs is equal to 0 to infinity xt e to the power minus st dt. So this limit is changed from 0 to infinity now. Earlier it was from minus infinity to plus infinity. Now it is from 0 to infinity. So it is only defined for positive time duration signals. So it is defined for causal signals, you can say, which signals are defined for t greater than 0. So this equation can be directly used instead of using the previous equation. So inverse Laplace transform from the given Laplace transform of a signal which is in S domain. So if x is given, we have to find the time domain signal xt by using the inverse Laplace transform formula as given in this equation. Xt is equal to 1 upon 2 pi j integration sigma minus j omega to sigma plus j omega and xs e to the power st ds. So here the integration is with respect to s, so that is why we are writing ds. Earlier it was dt, as we are doing time domain integration. The relation that we are discussing, the relation between Laplace transform and Fourier transform, since these two are used for same type of signals, so one is considering both stable and unstable system, which is done in Laplace transform, and Fourier transform is used for only stable system. So the equation that we have just derived for Laplace transform is xs is equal to minus infinity to infinity xt e to the power minus st dt. So in this equation, this s is the it is representing the complex frequency. S is equal to sigma plus j omega. So this is a complex number, a plus iv form. So sigma is a constant and omega is the frequency term. So this s is overall as a complex frequency, you can say. So this s is known as S plane also. It is given by Simon Laplace. His name is, this is the mathematician who discovered this Laplace transform. So that is why this S is the letter coming from his name, Simon. Okay. So now in this equation 1, if you put sigma is equal to 0, then for S is equal to sigma plus j omega. So sigma 0 means S will be equal to j omega. So the equation 1 can be rewritten for sigma equal to 0 as x of, instead of s we are writing j omega. We are replacing s is equal to j omega in equation 1. So x j omega is equal to minus infinity to infinity xt. So this s we can replace as j omega t dt. So this equation number 2 is a standard equation for Fourier transform of signal xt. Okay, so that is why we can say that if sigma is equal to 0, then we can convert, we get the Fourier transform of the signal xt, and if it is sigma is not equal to 0, then we are getting the Laplace transform. So this is the interrelation between these two transforms. The concept of S-plane, we're saying it is a plane because this consists of two direction or dimension, you can say. So S is equal to sigma plus j omega. So sigma is a constant and it is a real number, so it is plotted in the real x-axis, sigma, and the j omega is plotted in the imaginary y-axis. So this y-axis is representing j omega and x-axis is representing sigma. So this plane, this two-dimensional plane, is known as the S-plane, and it consists of poles and zeros of the Fourier Laplace transform equation. Okay, so in S domain, so convergence of Laplace transform or region of convergence. So we know that Laplace transform xs is given by the equation minus infinity to infinity xt to the power minus st dt. So that value should be, the magnitude of that overall integration should be less than infinity, so that the transformation output becomes a finite number. So then we can say that it is a converging. Okay, so this integration, if we replace s by sigma plus j omega, then we can get like this, minus infinity to infinity xt to the power minus sigma t. So this we're keeping this side, and okay, so one small mistake we can observe here, that this should be equal to, so this integration minus infinity to infinity xt e to the power minus sigma t, if we keep here, and e to the power minus j omega t, if we take in the right hand side in the denominator, then we can write infinity by e to the power minus j omega t. So this value ultimately becoming infinity. Okay, so this integration can be also written as minus infinity to infinity modulus of xt to the power minus sigma t dt is less than equal to infinity. So here, for conversion of the Laplace transform, we can get this condition. Okay, so here in this equation, if you observe it to the power minus sigma t, this may be a decaying or growing depending on whether sigma is positive or negative. So if sigma is positive, e to the power minus sigma t will be a smaller value, and if sigma is negative, then e to the power minus sigma t will be a greater value. That is why it will be growing. Okay, so convergence will depend upon the value of sigma. So those values of integration minus infinity to infinity xt to minus st dt, for which the value is less than infinity, that will give the convergence, and those values are known, the range of those values are known as the region of convergence. Okay, or indirectly in this integration, if we put say s is equal to sigma plus j omega t, then we ultimately got this equation 1, and from equation 1 we can also say that the value of sigma for which equation 1 converges is the region of convergence for the Laplace transform of xt. So in this diagram we have plotted some random poles for Laplace transform of signal, suppose. So these cross symbols indicating poles. Poles means if there is a transfer function hs, suppose, and the values in the denominator, and the value for s which hs becomes infinity is known as the poles, and the value of s for which hs becomes 0 is known as zeros. So in this case, when we are analyzing the region of convergence, we look at the poles. So suppose these are the poles at different points 2 4 6 8, or minus 2 4 minus 4 minus 6. Okay, so 1 2 3, these three regions that I have indicated here. So these regions can be characterized or denoted by this equation. Suppose for this region of convergence of 1 will be real s less than minus 6. So this section will, this region of convergence is less than minus 6. So real s means sigma or real s, you can say less than minus 6. Similarly, this minus 6 to minus 4 region can be written as minus 6 less than real s minus 4. So there are some properties of region of convergence. So we quickly go through this. Suppose the region of convergence does not contain any poles. So you can see in this diagram, the region of convergence is between poles, or but it is not in the poles. On the poles means it is in between two poles. It can exist because in the poles, if you put the value of suppose minus 2 here, so if at 2 it will be equal to 0, s minus 2 will be equal to 0. If s is equal to 2, s minus 2 will be 0, so hs will be infinity. So at 2 it cannot be, this ROC will be unstable, or it does not exist. So do not define ROC in between in the poles, and it just define in between the poles. And ROC of xs contains strips parallel to imaginary geometric axis. That is what I have shown in this diagram, that ROC, suppose it is existing between two poles, so it becomes like a strip in the imaginary axis. So these vertical strips are known as the strips, parallel strips in the imaginary axis. ROC always exists between two consecutive poles that we already have discussed. If there exist n poles, then n plus 1 ROC exists. Okay, and then n plus 1 inverse Laplace transform also exists. If n distinct poles, there will be n plus 1 ROCs and n plus 1 inverse Laplace transform. So we have taken an example here. So we will quickly go through this. Find the region of convergence of x equal to e minus at ut. So for region of convergence, we have to obtain the first s domain representation of the signal, that is the Laplace transform of the signal. So if we put xt is equal to e to the power minus at ut, then we can get this equation. So since there is ut here, so it is a causal signal, and the integration limit becomes 0 to infinity. And if we take common t here, then you can write minus s plus a to t dt. So this integration will result in xs is equal to 1 by s plus a. So for stability of this axis, we can say that s plus a is greater than equal to 0, because it should be non-zero and it is positive. Okay, so since the magnitude should be greater than equal to 0, so here if you put s is equal to sigma plus j omega, then we can write sigma plus j omega plus a greater than 0, or 0 plus j omega j0 we can write. So for similarity in both left and right side, we write this as 0 plus j0, ultimately this is 0. So if we compare the real parts, sigma plus j omega equal to 0, suppose greater than equal to 0, so sigma is greater than equal to minus a. That is minus a, if this is a point 0, then this the point minus a. So in the minus a, we are drawing a vertical line, and sigma greater than minus a is the region in the right hand side of this point, sigma equal to minus a. So this area sigma greater than minus a is the region of convergence for the signal, this e to the power minus a t ut. Okay, for this signal, the region of convergence for ROC is sigma greater than minus a. Okay, that means all the values in the right hand side of this a will be giving the stable output. So Laplace transform can be obtained for any value greater than minus